In this video, we'll be looking at the motion of charged particles in an electric field. So in this topic, we'll be looking at something called the electric potential difference. The electric potential difference is the amount of work done in moving a positive test charge from one point to another in an electric field. The electric potential difference is given the symbol of delta V. Now the units for the electric potential difference is joules per coulomb, or in volts. 1 volt is equal to the equivalent of joules per coulomb. Now the formula to work out the electric potential difference is delta V is equal to W on Q, where W is the work done in moving our positive test charge, and it's in units of joules. And our Q is our charge. So the normal units for W are joules, like I said. However, you'll be given some questions where you'll have electron volts instead of joules. So you need to be able to convert from joules to electron volts. So to convert from joules into electron volts, you need to divide by 1.6. Divide your joules answer by 1.6 times 10 to the negative 19. To convert from electron volts into joules, you multiply your electron volt answer by 1.6 times 10 to the negative 19. So you need to be able to remember these. So the 1.6 times 10 to the negative 19 is actually the charge of an electron, and it will be given on your formula sheet. Now consider a uniform electric field. So in this electric field I'm going to have 2 points. The separation of these 2 points will be given the distance of d. These 2 points are x and y. Y is positive to x. So since I've got a uniform electric field, the force that would be experienced due to this electric field is going to be given by the formula F is equal to QE. So this formula is just a rearrangement of E is equal to F on Q. So now we know what the force would be. So if I consider the work done by a positive test charge moving it from point X to point Y, if the potential difference is going to be equal to delta V between X and Y, and the distance is d, the work done, given by the formula for work, W is equal to Fs, or work is equal to force times by distance. So the work done is going to be equal to the force on our particle, which is going to be QE, times by the distance, which is d. So W is equal to QE d. From the formula I gave you before, we know that delta V is equal to W on Q. If we rearrange this to get W by itself, we get W is equal to Q times by delta V. Now if I make my formula that I derived before equal to this one, equate the two of them, I get that E d Q is equal to Q delta V. Now if I rearrange this to find out the electric field, so E, I get that E is equal to delta V on D, because our two Q's cancel each other out. And that is how we derive the formula E is equal to delta V on D. If we place charged particles in a uniform electric field, they experience a constant force. We know from Newton's second law of motion, F is equal to ma, that if we have a constant force, our particles must undergo acceleration. So therefore, if I have charged particles in an electric field and they experience a constant force, therefore they have an acceleration. So the magnitude of this acceleration can be found out using Newton's second law and using F is equal to EQ. Now if we go ma is equal to EQ, just by making the equivalent of each F's, and rearrange that, we get that the acceleration is equal to the electric field strength times by the charge of our particle divided by the mass of the particle. So this acceleration is going to be in the same direction as our force that we experience. To help us understand the motion of a charged particle in an electric field, let us use some analogies from projectile motion. So I'll use some examples that you should be familiar with in this section now.
So I have here a projectile launcher which I've set up so it's horizontal. So if I launch this ball now in a horizontal direction, we notice that the ball goes in a downward direction. So this is due to the gravitational field of the Earth. So now let's compare this motion to the motion of a charged particle in an electric field. So what I have here is a cathode ray tube. In a cathode ray tube we have a beam of electrons being produced. So if I apply an electric field to this, we get a deflection of these electrons. So we can see I've got a negative charge being placed on the top plate, which is causing the electrons to move away from that. If I move this electric field to make it so it's in the opposite direction, you then get the movement of the electrons in the opposite direction. So the electrons want to get away from the negative charge plate, causing a deflection. So if we compare this to our projectile motion, we'll see that the movement of the electrons through the charged plates is similar to the movement of our ball in our gravitational field. So knowing that our deflection of our charged particles and our projectile motion behave in similar ways, we can apply the same formulas from projectile motion to calculate changes in our moving charged particle.
So the key points for the video. The potential difference, or delta V, is the work done per test charge over a distance, so between 2 points. We can say this in the formula of W is equal to Q delta V. We can rearrange this formula to find out delta V. In that case, delta V would be equal to W on Q. Now, the units for work can change in this section. So normally work is measured in joules, but you might need to change it into electron volts, or from electron volts back into joules. In that case, to change from electron volts into joules, you need to multiply by 1.6 times 10 to the negative 19. If you're going to change from joules into electron volts, you need to divide by 1.6 times 10 to the negative 19. You need to know how to derive the formula E is equal to delta V on D. So the electric field is equal to the potential difference divided by the distance. So that derivation was in this video. Make sure you know how to do that. So the motion of a charged particle through an electric field is similar to that of projectile motion. And as such, we can use the formulas that we know from projectile motion in analysing the motion of an electric field, a charged particle moving in an electric field. So there'll be more videos on the actual calculations of that, but for now, you just need to know that we can use the same formulas. And that is it on the motion of charged particles in an electric field.